Question 2, Part C. The diagram shows points P, 2t, t squared, and Q, 4t, 4t squared, which move along the parabola x squared equals 4y. The tangents to the parabola at P and Q meet at R. Part 1. Show that the equation of the tangent at P is y equals tx minus t squared. In order to find the equation of the tangent at point P, I need the coordinates of the point where the tangent contacts the parabola, which we do know, which is 2t, t squared, but we also need the gradient of the tangent at that point. So I'm going to find the gradient function of the parabola x squared equals 4y and then use that to find the gradient of the tangent and then use the point gradient formula to find the equation of the tangent at point P. So I'm going to rearrange this equation here to make y the subject. So y is equal to 1 over 4 times x squared. Differentiating y with respect to x, we get y dash is equal to 1 over 2 or half times x. Now at the point where x is equal to 2t, that's the x coordinate of point P in parametric form, we substitute 2t for x, we get y dash is equal to half times 2t, which equals t, which happens to be the parameter itself. Now the equation of the tangent at P with coordinates 2t, t squared, we use the point gradient formula. Y minus y1 is equal to m, or the gradient, which in this case is going to be t, times x minus x1. Now our x1 is 2t and our y1 is t squared. So substituting those values or those terms for x1, y1 and m in the point gradient formula, we get y minus t squared is equal to t multiplied by x minus 2t in brackets. Now I'm going to expand the brackets on the right hand side and move the negative t squared over to the right hand side at the same time, and we get y is equal to tx minus 2t squared plus t squared. We can combine like terms here, so we'll end up with negative t squared. Therefore, y is equal to tx minus t squared as required. Part 2. Write down the equation of the tangent at Q and find the coordinates of the point R in terms of t. Repeat the process in part 1 to find the equation of the tangent at point Q. Now at the point x equals 4t, the gradient of the tangent y dash is equal to half times 4t, which equals 2t. Again, we're using the gradient function y equals half times x to find the gradient of the tangent at point Q. Now the equation of the tangent at point Q with coordinates 4t, 4t squared is found using the point gradient formula, again like we did in part 1. Y minus 4t squared is equal to 2t outside of x minus 4t in brackets. Expanding the brackets and moving the negative 4t squared over to the other side so it becomes a positive, we get y is equal to 2tx minus 8t squared plus 4t squared. We can combine these two terms since they're like terms, and we get y is equal to 2tx minus 4t squared. Now to find the coordinates of point R, we solve the equation we found in part 1 with the equation that we found in part 2 simultaneously. And we can use the substitution method for that. Now if you recall in part 1, we got the equation of the tangent at point P is y equals tx minus t squared, and the equation that we just found is y equals 2tx minus 4t squared. So we're going to solve tx minus t squared is equal to 2tx minus 4t squared to find the x coordinate of point R. Once we find the x coordinate, we can use either one of the equations that we found to then find the corresponding y coordinate, since point R is a common point on both tangents. Let's go back to our simultaneous equation. So I'm going to move the terms involving tx over to one side. So I've moved them over to the right hand side. So we have 2tx minus tx gives us tx on the right hand side. And on the left hand side, I've left the negative t squared there. I've added 4t squared to it. And we get 3t squared on the left hand side. So dividing both sides by the parameter t, of course assuming t is not equal to 0, we get x is equal to 3t. So I'm going to use the equation from part 1, y equals tx minus t squared, to find the corresponding y coordinate of point R. So y is equal to t times 3t minus t squared, which equals 3t squared minus t squared, which simplifies to y equals 2t squared. Therefore, the coordinates of r are 3t, 2t squared. Part 3. Find the Cartesian equation of the locus of R. Note, the locus of a point refers to the equation of the path that the point follows as the parameter is varied. Find the Cartesian equation of the locus of point R by solving the parametric equations simultaneously. And we do that by eliminating the parameter t by substitution. Now, if you recall from part 2, the parametric equation of point R is x equals 3t, y equals 2t squared. So let's start with x equals 3t. Let's make t the subject. So I'm going to divide both sides of this equation by 3, and we get t is equal to x over 3. Now let's move to the equation for y. We have y is equal to 2t squared, but we just found that t is equal to x over 3. Now the Cartesian equation directly links the y with the x and eliminating t altogether. So I'm going to substitute x over 3 for t here. So we get y is equal to 2t squared, which equals 2 times x over 3 in brackets squared, and expanding the brackets, we get the Cartesian equation y equals 2x squared over 9.